All right, so we're going to pick up with where we left off last time. We had discussed last time double integrals over polar regions, right? And now we're going to get into some of the applications of double integrals. We have already seen one application of a double integral, which is let me get your lecture thing up here. Anybody remember the one application of a double integral? I mentioned something about if you want to find the area of the region. No. So we did see one application that if you did a double integral over some region R of 1 with respect to area, that was equal to the area of R. We did see that. That is an application. You can use a double integral to find the area of a two-dimensional shape, lamina, something like that. Right, so you could verify the formula for the area of a circle this way. All right, so that's one application, but today we're going to do some others. So first of all, remembering what density is, or remembering maybe it's the first time you're thinking about it. Density, the density of something is the mass of that something divided by, in this case, area. Now, we're talking right now about a two-dimensional sheet, something like that. So we're going to look at like a sheet of paper, which we're going to call lamina, and imagine that this sheet of paper has density at every point. So at every point, you get like a little infinitesimal point there, and you look at the mass of that infinitesimal point divided by the little infinitesimal area, and that would give you the little infinitesimal density. Okay, so we can, let's say we have something where we can measure the density at every point, and the density is different. If the density is the same throughout the lamina, we call it a homogeneous lamina, meaning that it's all the same. A sheet of paper is probably a decent example of a homogeneous lamina. We can assume that the density of this paper is pretty much the same throughout the paper. But if we could measure very accurately, we would know that the density is different at every point, right? Because it's not perfect. The wood fibers are different in different locations of the page. But if we can all agree upon the idea that when we measure density of a two-dimensional sheet, it's just the mass divided by the area, then we can come up with a formula for the actual mass of the lamina to find its total mass. The total mass comes from, can you all see this okay? And I was all happy about this projector, and then I realized some of my stuff doesn't come out very good on it. Please turn in your take-home if you don't have it, if you haven't done so. So if we take a lamina and we cut it up into little infinitesimal rectangles where the width is dx, like we've always looked at it, and the height is dy, then dA is going to be dx dy, right? That's the little infinitesimal area. Density is mass divided by area, which means if we multiply both sides by area, the mass is density times area. So the mass will be this thing, dx dy. So what is this right here? It's a function which we call a density function. So that's a function someone would have to give us that tells us what's the density at every point on this lamina. If somebody tells us the density at every point, we should be able to come up with the total mass of the entire thing. So if this is the mass, which is the density times the area right here, and that's just the mass of that little infinitesimal rectangle, then we add them all up, that's a double integral, right? So we do a double integral over d is this region, of the density function times dA, which is the dx dy. So another way to look at it, to not make it so complicated with density and you know, trying to come up with this mass area relationship, is just think that you have a sheet, right, which used to be our ground. We used to have a function on top of that, right? And we would look for the volume, so we'd measure the height at each of those points and then measure them all, and you would get this total volume. What we're really doing is going to every point here and imagining that at that point it has a mass, right? And we measure that mass and give it some height. So if the mass is 2, it's out here. If the mass is 3, it's out here. If the mass is 10, it's out there. Well, if you take all those heights, then that volume is really the mass. So we're assigning a value to the mass at each point. And this is, that'll give us a total mass. All right, I hope that makes sense. Another way you could approach the same type of problem is that you have, or a totally different problem, but the same double integral is going to form here, is if you have a lamina, two-dimensional again, and at each point on the lamina you have some electrical charge there. Then you can look at your charge density as being sigma xy, and then your area at that little in that lamina as being dA. And so if you want to add up all of your charge densities, you get your total charge. So again, you would have to know the charge at each place, but then you get the total charge of the whole sheet, the whole lamina, by doing a double integral over that region. You just need to know the sigma xy. And this is not the only two applications. You can extend this to anything, really. This is just two specific ones: finding the mass of something, finding the total electrical charge. So let's try this. A lamina is formed by the region bounded by y equals 1 minus x, y equals 1, x equals 1. The density at a given point xy is given by the density function xy. Find the total mass of the lamina. So let me put where our bounds are. We have y equals 1 minus x, y equals 1, x equals 1. The density function, rho xy is xy. So I first need to come up with the region. The region is given to me right here. I can call it R or D, it doesn't matter. D for domain, if you wish. I'm going to graph this. Y equals 1 minus x, so I have an xy plane here. Y equals 1 minus x looks like this. Y equals 1 is a horizontal line like this. And x equals 1 is a vertical line like this. And so we're looking, it says here, a lamina is formed by the region bounded by these curves. So our region is this one in here. Everybody agree with that? That's our D. At each point on this lamina, there is a density, right? The density here is given to us by x times y. So wherever you are here, you take your x coordinate and divide it by your y coordinate, and that's, multiply it times your y coordinate, and then that's the density at that point, right? So we want to add up all those density times the areas to get our masses. So what is our double integral going to look like? What type region do you want to treat this as? Type 1, type 2, polar, what? This is Cal 3, right? I'm in the right class? Yeah, okay. Type 1? Type 1, if we do type 1, then we're doing it like this, where we have top function, the bottom function, and then our limits left and right, I think we're pretty clear, are stuck between, 0 and 1. Our top function would be y is 1. Our bottom function would be y is 1 minus x. So I know that my x's were bounded between 0 and 1. My y's were bounded between 1 minus x and 1. Y'all following this? Setting up my limits for my variables. And now I just need my double integral. 0 to 1, 1 minus x to 1. And then what's the integrand here? We're going to do the density function, right? X times y. And then dy dx. And we're there. We compute this. That's our mass. I won't do it, but yes. So it's pretty basic setup, nothing special here, right? Questions? If we wanted to know the actual unit, right, for the mass, we would have to be given some information about, how the density is measured. So we'll leave it unitless as we always do. All right, let's see what's next on our set of examples. The charge is distributed over the region bounded by y equals 1 minus x, y equals 1, x equals 1. That's the same exact region, right? Such that the charge density at xy is given by sigma xy equals xy. Find the total charge. So what is this? Same exact answer, right? Except now your answer is the total charge instead of a mass. So the only difference between the two problems is just the meaning of the answer, right? That's all. So I'm not going to go through this again. It's the exact same double integral because it's the exact same region, and your charge density here is the same as the density function was for the mass. So nothing to do here. Yeah, it's changing what it is you're measuring, right? I mean, I can tell you, yes, this is the mass of something, or I can tell you this is the total charge on that. The numerical answer would be the same. All right, so suppose we have a lamina in the xy plane. Same thing. The moment of the lamina about the x-axis. Have you all heard of moments? Moments of inertia. Okay. A moment of the lamina about the x-axis. So look, here's the x-axis right here, right? The moment about the x-axis, capital M sub x, is the double integral over d of rho of xy. That's the same. dA is the same. The only difference is this right here. So what you're doing, if this rho of xy, dA gave us the infinitesimal mass at the points, right? Multiplying it by y means that you're looking, let's say where my arrow is, you're looking right there at the infinitesimal mass, right? That's what that rho of xy dA gives you, right there. And then you're multiplying it times y. Now where's y? It's the y coordinate, the distance from the arrow down to the x-axis. So not only are you looking at the mass, you're looking at the mass times its distance from the x-axis, which becomes important because what we're leading up to is what's called moment of inertia, which is the object's resistance to movement, rotation around the x-axis. So if you have this lamina, let's say you want to spin it around the x-axis, it resists your motion, right? All objects want to stay at rest unless, right, you have to apply a force. So if I try and push this thing, imagine it has to swing around the x-axis. If I push it, it resists that, right, because it has a mass. So it resists that motion. Now, if I try and push it, is it going to be easier for me to push it if this is further away or closer to the x-axis? Closer? What would be easier? What do you think? Would it be, if I got my finger here and this thing had to swing around the x-axis, it has a certain mass. If I got my finger and push this and try to push it around, right, then would it be easier to push this from here? Or if I took the whole lamina and moved it up to the top of the room, push it from there? What would be easier? Move it to the top of the room? What do y'all think? So one of the analogies is if I come over here to the door, right? Now this is like spring-loaded. So if I come over here and I try and open it, right, I can push on it with my thumb and open the door here, right? The axis of rotation is the hinge here. This has a mass. I'm further away from the axis of rotation here. It's pretty easy for me to open. Now, if I put my thumb right here and try and open this door, right, it's almost impossible to do. I have to come out here a little further, right? So it's the same sort of idea as we're trying to build up to this idea of an object's resistance to motion, a resistance to rotation along certain axes. So it makes sense that we would need in that to measure the distance from that infinitesimal mass to the axes, which is what the moment of the lamina about the x-axis is all about. All right? So all you're doing here to do your moment about the x-axis is measuring the distance from that little mass to the x-axis, which is your y-coordinate. The moment of the lamina about the y-axis is the exact same thing, except now you're looking at the y-axis, so your distance to that axis is actually x instead of y, right? So that's from this point to the y-axis, that distance is x. Okay, got that? Now, if you have the moment about the x-axis and the moment about the y-axis, then you can actually find what's called the center of mass of the lamina, which is what? Center of mass. For a lamina, it would be like its balance point. I don't have a good lamina I can put in here, but you know, if this were a rigid lamina, rectangle, then the center of mass would be a point that I could basically balance the entire thing on that point, right? So what we could do is we could look at this entire lamina as being just a point instead of this whole big shape. So that center of mass, in this case, lives somewhere in that lamina, doesn't it? Yes, and we can find the actual coordinates, we call them x bar and y bar, of where that center of mass is. Now in Cal 2 you probably did this, but when you do it in Cal 2 you assume that the lamina is homogeneous. You don't assume that the density changes throughout the lamina. See, here we can actually have a varying or a variable density and still find a center of mass. So to do it, we have to compute this. For the x-coordinate of the center of mass, you need to calculate the moment about the y-axis and divide it by its mass. So here's the moment about the y-axis. And then 1 over mass is dividing by mass. But remember, mass is its own integral, isn't it? So to do x bar, you need to be able to compute 2 different double integrals. And then to do y bar, you need the moment about the x-axis and then divide by mass. So to do total center of mass for a non-homogeneous lamina, you need 3 double integrals. Moment about x, moment about y, and mass. If you get all 3 integrals, you're in business. With me? There's just slight variations on the integrals, though. Does the center of mass of an object, a lamina, does it have to be on the lamina? Is it possible to have a lamina whose center of mass is not on the lamina? What? What's a good example of one? 2-dimensional. How about that? Now, I think we would all agree that that would be good if it was homogeneous, right? You might be able to come up with the non-homogeneous where the center of mass is on here, but if this was homogeneous, the center of mass is in the center, and that's not on the lamina. So I'm talking about this was our lamina, right? It's like a washer. So it is possible to have a center of mass not on the actual object. It's perfectly fine. So we just shouldn't be surprised if that ever happens and not, be like, oh my gosh, I'm wrong. It can happen. All right, well, I think there's probably an example now. So find the center of mass of the region bounded by this. So I'm going to do a lot of this on Mathematica. I'm just going to really set up the integrals. So we want to find the center of mass of the region bounded by x equals 0, y equals x, 2x plus y equals 6, and the density function is given by x squared. So I'm going to start with my picture. X is 0 is the y-axis. Y is x is our diagonal. And then 2x plus y equals 6 can be rewritten as y equals negative 2x plus 6. So that's going to be like up here at 6, down 2 over 2, down 2 over 2, something like that. Not very good. That's better. Everyone agree with that region? Right here? I need to do a double integral on that. Type 1, type 2, what do you think? Type 3, type 4? No. Type 1, type 2, polar, right? So what do you think? You could do type 1 or 2 here, right? I like type 1 only because if I look at type 1, I have a function on top and a function on bottom. My x varies between two constants, and the one on top and bottom stay the same the whole time. If I were to have looked at it as a type 2 sideways, like this, then here it's the green one and the black, or yeah, the black one, top and bottom. But then when I get to that point, it switches. Now the red one's on top and the black one's on top. So I don't want to switch and have two different integrals, so I'm not even going to mess with that. So I'm going to go type 1. What piece of information do you think we still need to get here, though? Like, I know which one's on top. I know which one's on bottom. The intersection, right? I need to figure out where they hit each other so I can figure out what that point is. I know it's going to start at 0, so I know my x is bounded between 0 and something. So what's the intersection point? 2? Yes? Okay. I'm not going to go through it, but it's 2. You're just setting y equals x equal to y equals this. So set this right here equal to x, and you solve and you get 2. Is that all right if I don't show that, or? Yeah. What about my restriction on y? Between it's the top and bottom function. Careful. If you go 0 and 6, it's going to be a rectangle. It's not going to be this region, right? Your top function is this one, right? Your bottom function is this one. So x in what? Negative 2x plus 6. Right? This little arrow thing is stuck between x right here and this top one, which is negative 2x plus 6. Your x values are stuck between 0 and 2. Okay, let's get everything together here, okay? We're going to have 3 double integrals. We're going to have a mass. We're going to have a moment about, it doesn't matter which one I do first here. I'll do moment about x, and then I'll do moment about y. So what's our mass integral? Double integral, 0 to 2, x to negative 2x plus 6 of what? Density function, which was x squared here, right? So x squared dy dx. Okay, good. It's dy dx because it was a type 1. All right, a little more room. I'll figure that out with Mathematica in a second. The moment about the x-axis is the same integral, right? With one little thing added. Let's see. So what is it? If you do the moment about the x-axis, you multiply by y. It's opposite of what you think. Not what you think, but just think about it. That's the axis. You want to go up to the region, so that distance is y. So y x squared dy dx. And then the moment about the y-axis is integral 0 to 2, x to negative 2x plus 6. And now x times x squared, which would be x cubed, dy dx. I mean, these are little subtle changes, right? But it makes a huge difference with your integration. Oh, shit. Oh, great. What did I hit? Hold on a second. Oh, wait. You know, I'll use Mathematica. I won't use Wolfram. See if this comes back on. Okay. New one. So what's cool about this Mathematica is that I can do a double integral. Let me open this up so you can see it. Have I shown you how you put the double integrals in here? No? So here's a single integral, right? Inside where that expression is, I'm going to throw another double integral in there. See that? That's the way you do a double integral in Mathematica. So inside my expression is, and watch, I'm going to say m equals this. So I go 0 to 2, x to negative 2x plus 6, then just x squared, right? dy dx. 4. So the mass is 4. Now I'm going to copy this formula, paste. I'm going to call this mx. And the only difference is that I put a y in here, right? Y times 48/5. And then if I copy this again, y'all realize like the tedious part of this you would have to do on your own, right? Paste. And then my would be x here, 24/5. So now, what is x bar? By definition, yeah, x, I'll put it on the side here. X bar is m, which one? My over mass, right? And my we just got was 24/5. 24/5 over 4, right? Which is what? 24 over 20, which is, what goes into those? 6/5? 6/5? And then y bar is mx over m, 48/5. 48 over 20, 12/5. So about what? 6/5 is 1.2, right? This is what? 2.4? 1.2, 2.4? 1.2, I don't know, somewhere 2.4, I don't know, somewhere. I mean, it's somewhere in there, okay? So if I look at that, I might actually disagree with that looks like the center of mass. But what is the key to the problem? That doesn't really look like the center of mass. Yeah, it's not uniform density. This thing is more dense over here in this corner, right? Because our density function was x squared, wasn't it? So if I just look at this, go out to, let's say I go out to 1, then the density all along this line would be 1. If I go inside here to like 1/2, the density is what? 1/2 squared is 1/4. So you've got less density over here. Now you go past 1, between 1 and 2, now you're squaring a number that's bigger than 1, so it gets big. So a lot of your mass is over here, which is why it makes sense that your center of mass is more this way, to the right, than it is like maybe you would be thinking it would be like somewhere in here somewhere. Homogeneous, it would have been. So what if I said do the same problem with the homogeneous? How would you do it? Yeah, why don't you just put 1 in the integrand? Then you use a density function of 1. Or you could use a density function that's a constant, like k for constant. So the density is the same throughout the entire lamina. If you do that, then how would things change? Let's see, I'll replace it with 1. If I replace this with 1, are y'all following what I'm saying? Okay, replace that with 1, you get 6. Replace this x squared with 1, you get 16. Replace this x squared with 1, you get 4. So if you do what x bar is my over this, so what's 4 over 6? 2/3. And then you do 16 over 6, which is 4. So back to your picture, back to my picture, 2/3 would be somewhere around here, and then up to 4 would be like in here, I believe. Well, it's not drawn to scale, so it's kind of, but I think that makes a little more sense of it being homogeneous, that I'm further this way than I am this way. Y'all follow what I'm saying? Okay. Yes? All right, what's next? Okay, so the moment of inertia is different. The moment is one thing, the moment of inertia is something else. The moment of inertia about the x-axis. So again, your rotation is about the x-axis now. That's what we're talking about. Is squaring that distance. That y we had earlier, right? Capital M sub x was y times our density function, right? This is y squared density function. The moment about the y-axis is x squared density function. The moment about the origin, the moment of inertia about the origin is I-O for origin, and it's just the sum of the two moments the other direction, around the x and then around the y. The moment of inertia of a particle is its mass times its squared directed distance from the x-axis, or from an axis. So it's just another computation, right? Just throwing in another x or another y. That's it. There's no more notes here. Questions? Well, this, let me go back to the first, yeah. This unit in here is a mass, because it's density times area. Your density is mass over area, so mass is density times area, and so this times this is a measurement of mass. So you're integrating masses to get a total mass. the sum of masses. So whatever this unit would be, these would be like kilograms or something like that. And then you'd have a total mass at the end. I don't know, does that answer your question? Or, I mean, you could look at this as being density, which would be your kilograms per square inches or something like that. But then you're multiplying it times area, which is like square inches. These square inches would cancel with those square inches, and so you just have mass. Make sense? So the integration doesn't take you back to a new dimension of unit. It keeps the same unit because it's adding them up forever. Yes? All right. That's it for 12.4. Don't know if, yeah, I don't have a homework there. I'll give you something. All right, triple integrals. So everything we've done with double integrals, we're now extending to triple. All right, so concepts, all the concepts are very similar, except now something has changed. All right. Whoa, why isn't that coming in? There we go. Remember the first region we started with in double integrals was a rectangle on the ground? We said, what if we take a region on the ground where we stick our x between two constants and our y between two constants? We said that's the simplest region we could possibly have for a double integral, right? We said that was a rectangle. And that, when we had that situation, we could even change the order of integration. It didn't matter because everything was between constants. We were all happy about that, and then I told you you'll never get a problem like that on your test because it's too easy, right? Well, we have to start kind of in the same place with triples. So very important to understand that this is where we were. This is where we were with double integrals, right? Our x's were between two constants. Our y's were between two constants. And now we are actually allowing our z to be between two constants. But this is just the domain of the function. The actual function lives in four-dimensional space. We talked about this last class. It was a long time ago. But so whereas before we looked at this right here and we looked at a surface above it and we found the volume down to it, right? So we looked at that as being the ground and then some surface above and how much volume is below it. Here, since this is now going to be a three-dimensional domain, I can't visualize the function. We just have to know that I'm going to take a point in here, I'm going to plug it into a function that's going to spit out a value. And I measure maybe the height of that somewhere. And then I take another point in here and I measure the height there. And then I take all the points in there, measure all the heights coming out of this function f, add those all up, and I get this what? What does it represent? Well, we can't really say volume anymore because it's not three-dimensional. So sometimes we call them hypervolumes to let you know it's like a four-dimensional solid shape, but forget it all. Let's just get to something that makes more sense to us now, hopefully, with that application from the last section. What if at each point in this solid, I measure its mass? Then wouldn't this triple integral represent the total mass of that thing? So we don't want to get ourselves locked into the idea anymore of trying to find necessarily like the volume under a solid. When we're in triple integrals, it's just impossible to visualize. I hope that all makes sense. Okay, so there's the most basic shape that we can have a triple integral over. It's like a cube, like a parallelepiped, three-dimensional box. Now, what I will point out to you is if we do have a three-dimensional box like this, look at its shadow on the ground. So if you were sitting there with the light shining it from like the z-axis way up at infinity, shining a super bright light down, its shadow would appear to be a rectangle on the ground, right? And so its rectangle on the ground, the shadow, is going to be like a rectangle from a double integral. Yes? That's going to be the key to doing a triple integral, is we look at the solid that we're trying to integrate over, the three-dimensional solid, and we visualize its shadow on the ground. Its shadow is the double integral. And so that third of the triple integral, that third integral, is only going to be controlled by the top of this and the bottom of this, as you'll see. Let me go to my next picture. So let's suppose that E is a box where X is stuck between two constants, Y is stuck between two constants, Z is stuck between two constants. Then the triple integral over E, over that box, of f of x, y, z. So here you can see our function, right? Our hypersurface is a 3 variables go in. One value comes out. It's a 4-dimensional thing. We can't visualize it easily. But look at our d. What is that? Instead of dA, it's dV, because that little differential was our length times width times height of the little infinitesimal piece of that box. So we've added a third dimension in here, which is why we have dV. And then what it becomes is triple integral dz, dy, dx. Notice that the order of the integration, we have an inner integral with our restrictions on z, goes with dz. Then a middle integral, restrictions on y, goes with dy. And then our outer integral, restrictions on x, go with x. Do you think you can switch the order of this around? Since they're all constants, right? Seems like you could. And that turns out to be the case. Because they're all constants, you can switch it around. But because there's 3 variables, there are a total of 6 different triple integrals that you could do that would all give you the same answer. You could go, let's see, do I put them here? No. I could go dz, dy, dx, dz, dx, dy, dx, dy, dz, dx, dz, dy, dy, dz, dx, dy, dx, dz, right? I could switch them all, right? There's all those different permutations of the order. So it becomes a little more distracting, doesn't it? Just be aware you can do any order you want. Okay, so now here's an example. Evaluate this triple integral. All I'm going to do is set it up, and then, well, I guess I'll go through. It's our first one. There's some notation here I want to make sure we're all okay with. When you look at this, and you say you see this like closed interval, cross closed interval, cross closed interval, that's always in order, x, y, z. So this is your restriction on x, your y, and then your z. So I'm trying to do triple integral over e of x squared y z dv on that 0, 2 cross 1, 2 cross 0, 1. So that will turn into, see, these are my x's, my y's, and my z's. So it doesn't matter what order I go in, right? Because they're all constants. It does not matter the order, but I'm just going to go kind of what we've been doing. I'm going to go x on the outside, then y, and then z on the inside. So I'll go 0 to 2 here, 1 to 2 here, 0 to 1 here, and then x squared yz, then dz, dy, dx. Are we going to have any issues integrating this with respect to z? I don't know. Are you? So here's what I'll do. I'll break the problem up into 3 integrals. I told you I like to keep it all together, but some people like to break it up. I'm going to show you how to break it up and put it back together, just so you've seen them both. The inner integral, I'm trying to find integral 0 to 1 x squared y z dz. What is the antiderivative of x squared yz with respect to z? X 1/2 x squared y z squared, right? Evaluated from what 0 to 1? Z equals 0 to z equals 1. So just make sure you remember that what you're plugging in, what you're replacing here, because you have 3 variables, right? You need to remember which one's getting replaced with 0 and which one's getting replaced with 1. It's the z value. So if z is 1, this becomes 1/2 x squared y. If z is 0, what do you get? 0. So your answer here is just 1/2 x squared y. That's your inner integral. Now I'll do the middle integral. The middle integral is the integral from 1 to 2, right, of this thing that we just got, right? The inner integral turned out to be this. So 1/2 x squared y dy. So the antiderivative here, again, antiderivative of y is 1/2 y squared. Comes out, you get 1/4 x squared y squared. I'm evaluating from 1 to 2. And what's 1? Y. Y is 1, y is 2. If we plug in for y, we plug in 2, we get 2 squared is 4. 1/4 of 4 is gone, so you just get x squared. If I plug in 1 for y, I should just get 1/4 x squared. Everybody follow what I'm doing? It's very mechanical. There's not a lot of magic happening here. Yes? And now x squared, take away 1/4 x squared is 3/4 x squared. And now we go to the outer integral, which is 0 to 2. So the outer integral 0 to 2 of what I just got, which was 3/4 x squared dx. And now you're back in Cal 2. So this is going to turn into 1/4 x cubed, evaluated 0 to 2, which is what? 2. That was just to get you used to the setup doing the, inner, middle, outer. Questions? Now, those are very boring triple integrals whenever you have constants on all your variables. So instead, let's take a look at a particular solid here. This is a kind of a weird shaped solid. Let's see if my computer can keep up with me here. That is definitely not a box, right? It's not a box. But notice, oh, hey, get out of here. Notice that if you were able to shine a light on it and look straight down on it, like that, then you would have something that looks like I don't like that. That. Okay? I'm looking straight down. That solid is in there, right? We're looking straight down. Notice that its shadow on the ground is a type 1 region from double integral, isn't it? That's a type 1 region. My x's are between two constants, a and b. My y's are between two functions of x. And now, pop this thing out, turn it Bring it. Come on. Okay, can you all see my restrictions on my x's and my y's down here on the ground now? And notice that my actual solid has like a cap on the top and the bottom, right? The cap on the top and the cap on the bottom are actually surfaces, right? The top cap, there we go. There's the top cap by itself. Do you see that? That top cap is its own surface. The bottom cap is its own surface. And since they're both surfaces, the top one we could call U2 of xy, the bottom one U1 of xy. And if we fill in the middle, of course, that's just all the crap between it, but that's our solid, yes? Do you all follow that? So let me get back to this. Our x's are between two constants, right? Our y's are between two functions of x, and our z's are between two functions of x and y, because they're surfaces, they have to be functions of two variables, right? Yes? That is going to be a certain type of triple integral. We could start getting to like type 1, type 2, you know. We get all these different types, but the bigger picture is to understand that they're calling it type 1 in the book. Our x's are between two constants, our y's are between two functions of x, our z's are between two functions of x and y. If we have that case, then what does the triple integral become? Well, the triple integral over e of some function, which we haven't even talked about. Remember, this function f has nothing to do with that solid. It has nothing to do with the caps, right? This f is some hypersurface in four-dimensional space. I'm at 25%. I'm still going here. All right. So look at the way this integral sets up. Outer integral, a to b. Middle integral, g1 to g2. So there's our restrictions on our y. And then our inner integral is our restrictions on our z. Here's the function we're integrating, dy, dz, dx. Do you think you can change the order? Absolutely not, right? There's no way you're changing that order of integration. So it is what it is. You got to work with it, okay? Any questions? All right, let's see if we can do this one. Let me see how much this charge I really have. I have a feeling this thing's going to die on me. Let me see if I can switch the battery real quick without messing up. Oh, yeah. Okay, let me see if the recording's still picking up my audio. Looks good. All right. Evaluate this triple integral where E is bounded by the plane. So I think the hardest part of this is going to be figuring out what your region E is, like trying to draw it and stuff. I mean, if you did the problem, I know I got a couple of people ask me about one of the problems from the take-home where you had, I think it was like a paraboloid and a tetrahedron, trying to, you know, it's, I mean, imagine now, just your domain is that thing now, that three-dimensional thing. So let's try this one. You have triple integral. We're trying to do, we're trying to do triple integral over E. Do you think that there's like quadruple integrals? What do you think? Yeah, of course. But then the geometry of things gets really, really odd because here we can't even visualize the hypersurface, right? The function we're trying to integrate, we can't even really visualize it. We can visualize its domain because its domain is a restriction on x, y, and z, so that's three-dimensional. If you go to a quadruple integral, then your domain is 4-dimensional. So then you can't even visualize that. But it makes perfect sense to have something like that. It's just because you can't visualize it doesn't mean that it doesn't have some meaning to it. Okay. Let's find our region, because this is all about setting up the limits, isn't it? It's figuring out the limits of integration. Like on a test, when I'm grading it, I'm looking for your limits of integration to be correct. I mean, that's really it. You got all those right, the integration, cares about that. We can figure that out. So let's see. What the hell is this solid? X equals 0. What does that look like? It's a line, but see, now our E's in 3D though, right? So X equals 0 is actually the YZ plane, right? Y equals 0 is the XZ plane, and Z equals 0 is the XY plane. So remember at the beginning of the class, we said that the origin was the bottom corner over here? X came out that way, and Y is this way, and Z is up there. We have that wall, and the floor, okay? That's 3 of the planes that are enclosing our region, E. And then we have this 4th equation, which is a plane. So I'm going to try and draw it. Here comes 3D. X is coming out at you like this. Y is out this way, Z is out there. That's perfectly fine because that follows the right-hand rule. I know that this XZ plane here, XZ, I know this wall right here. Can y'all see that? This wall and then the floor. So now I just need to figure out where this plane comes into play here. So why don't I just pick some points? How about I let Y and Z be 0? So let my Y coordinate be 0. Let my Z coordinate be 0. What's my X coordinate then? 2, right? So I know that I come out X2. That is a point on that plane. I'm trying to get 3 points on this plane because if I have 3 points on a plane, I can define the plane, can I? All right, now let's let X and Y be 0. If X and Y are 0, what's Z? 4. Point up there. And now let X and Z be 0, and Y is 2. So I know my plane passes through here, right? And so what I could do is connect these. And that region is actually a tetrahedron, isn't it? It's a tetrahedron. That's E. Now remember what we have to do in order to do a triple integral. We have to figure out a way of looking at our region, 3-dimensional region. We have to be able to identify its shadow on the ground and look at that as type 1 or maybe type 2, it depends. We need to look at its shadow, and then we also need to look at the top cap and the bottom cap of the region. So by looking back at this, can we start discussing the shadow? Why don't I draw it over here? X, Y. Its shadow is just that triangle on the base of the tetrahedron, isn't it? That's our region on the ground. So we need to figure out what this line right here is in this picture. I know it's on my y-axis it was 2, right? On my x-axis it was what? 2 also. It came straight across like this. What is the equation of this line right here? Y equals... All you're doing is you're taking this equation and you're replacing Z with 0, right? Z is 0 means you're on the ground. Replace that with 0, solve it, and you get Y is Negative x plus 2? Is that what I heard? I thought I heard that. Y is negative x plus 2. Any questions on how I got this? This is our little region on the ground. It's our little shadow, right? It's our shadow on the ground there. And that, I think, is a pretty good type 1 region, isn't it? You have like a bottom function here. You have a top function. Give me just a second. Oh. That's our ground right here. I think we can say pretty clearly what our restrictions on x and y are, right? Our restriction on x is between 0 and 2. Our restriction on y is what? 0 to negative x plus 2. Now the only thing left to resolve is our restriction on z, which I'll put over here because this is our three-dimensional picture. So now we need to start talking about this solid over here. What's its top cap? What's its bottom cap? Well, the bottom's the easier one, right? What's the bottom? What's the surface? Z equals something that gives me that. What is it? 0, right? Z equals 0. So I'm going to draw a little arrow from the bottom of this cap. That is Z equals 0. That's the bottom of that thing. So that'll be this bottom limit. And then what's the top of this? So I'm talking about that face of that tetrahedron. What is the equation of that? It's got to be Z equals something. 4 minus 2x minus 2y. Because it comes from this plane equation, we solve the plane equation for Z, and that gives us our top. Yes? So this top one right here is like the U2 of xy, and this bottom one right here was like the U1 of xy. Does everyone see how this matches up with the picture that I had before? You have a top and now the picture I gave you, of course, was a little more elaborate than just a tetrahedron, but this kind of takes care of even crazy surfaces we could have, right? You have a top, you have a bottom, you have your type 1 region on the ground. Okay, so Z is between, back here, Z is between 0 and 4 minus 2x minus 2y. That's it. We're ready to set this up. We good? Questions? Triple integral time. We're going to go integral first from 0 to 2. Then the next integral is going to go from 0 to negative x plus 2. Then the next one is going to go from 0 to 4 minus 2x minus 2y. And what are we integrating? Y d dz dy dx. So I would start with the inner one. I think I'll just get this started. I'll just do the inner one and let you do the rest. The inner one will be integral from 0 to 4 minus 2x minus 2y. I'm integrating y with respect to z first. What is the antiderivative of y with respect to z? yz. We're treating y like a constant. I'm plugging in what here? 0 and 4 minus 2x minus 2y for what, though? For z. So this is going to be z equals 0 to z equals 4 minus 2x minus 2y. So first plug in this one, and then subtract what you get when you plug in that one. And so you should just get y times 4 minus 2x minus 2y, and then minus nothing. When you plug in 0, it vanishes out to 0. So, got that? I shouldn't say vanishes. It doesn't vanish. It's 0. I would probably distribute that y through. And that would be the integrand of my next integral, which would be the middle one. And we'll be doing that with respect to y, which will be nice because this will integrate pretty clean. And then we will be replacing y with 0 and y with negative x plus 2, finishing that out, and then integrating that with respect to x, replacing x with 0 and 2, and then you could finish it out. So it's pretty easy, again, to do it with Mathematica. You can do it all at one swoop. So it was 0 to 2. I'm only doing this in case you want to go home and practice this on your own. And then it was 0 to negative x plus 2. No, that's not. 0 to negative x plus 2. Then it was 0 to 4 minus 2x minus 2y. We were integrating y with respect to z, then with respect to y, then with respect to x. 4/3. Questions, comments, concerns? 4/3? Okay, so now, what if now you take a solid and you cast the shadow down, and this time, when you cast your shadow, your region looks like that. Now you're a type 2 region, right? That's a type 2 region from double integrals. You have that your y's are between two constants. Oh, where are they? Yeah, hold on. There we go. Okay, here's my x-axis, here's my y-axis. The y's are between two constants. My x's are between two functions of y, right, instead of two functions of x. And then my z's are still trapped between two surfaces that are both functions of x and y. So what's the only thing that's going to change here? Your outside and your middle integrals are going to switch, right? You're going to go dz dx dy instead of dz dy dx, because y is the one that has the constant, so it has to be last. And then the middle one would be the one with x. That's all dictated by the region on the ground. So here's the triple, C to D, H1y, H2y, U1 xy, U2 xy. Everything's the same except your order out here changed. This is just an extension, right, of what we already did. Let me do something. Let me go back to this for a second. This one right here that we did earlier, I said that's a type 1 region, didn't I? Could I have done that as a type 2 region? Yes. If we did, we should get the same answer, shouldn't we? What's the difference? Well, my y will be between what? 0 and 2, but now my x's are between two functions of y. What would those functions be? 0 and you just solve this for x, right? So it'd be x equals negative y plus 2, and then you switch it, your order of integration, and that'll be the exact same answer. So if I wanted to do this one as the other type, I just need to switch that in the integral, and it would come out the exact same. So this would be 0 to 2, this would be 0 to negative y plus 2, and then this would be dx and dy. That's what this next note was saying. I do not want to go through the process of doing this problem because first I have to set up the tetrahedron, right? And then I have to get the equation of the plane, don't I? Don't I have to get the equation of that plane? Which means you have to find two vectors. You have to cross them to get the normal vector. You have to do that on your take-home anyway, right? So I just don't want to invest the time in that. But does that seem like a fair problem that you could handle that? Yea or nay? Yes? Yes? Okay. All right, so triple integral over region E. To consider more possibilities, and we haven't talked about this. Everything so far, we've had this triple integral, the volume, and we cast the shadow down on the ground, didn't we? And on the ground we said, oh, is that type 1 or type 2? And we haven't even talked about what if the shadow's what? A circle, polar, right? What if, we will get to that. We're not there yet, okay? But we've just said the shadow on the ground is type 1, type 2. We haven't even talked about what if, I mean, why did I cast the shadow on the ground? Why not come in with the light from another direction, like the y-axis, and cast the shadow onto a different side? So imagine that you have a solid here. Here's your x, your y, and your z. Now this solid is all jacked up because if I look at this solid, try and look at it straight down from the top, right, like this, I would have some sort of, on the ground I would have this shape, right, which would be kind of like a type 1 or type 2 on the ground. But do I have a cap on the top and bottom of this if I'm looking top and bottom? Well, I might in this, actually. But yeah, there's a problem here because look, the shadow of this on the ground, you see how this curves here? And this curves here? So the shadow on the ground is actually not this front top part. It's actually more than that. So the shadow would be all weird. And so basically what I'm getting at is if you have a shape that looks like this, and you cast the shadow instead on the ground to the side wall, now you have on that side wall your y's are between two constants on that side wall. See them? You have that your z's are between two functions of y, and you actually have two caps on this thing, u1 and u2, that are functions of y and z instead of x and y. And so that could become a completely different animal, couldn't it? Yeah, so your integration, it would still be what? Your y's are between constants, your x's, your z's are between two functions of y, and your x's are between two functions of y and z. So you still have a triple integral, but now you're talking about, look at this integration here. C to d, okay, that was your restriction on y, so dy. Then your h1y, h2y is your restriction on z, so dz comes next. Then the inner one is your restriction on x, right? You see how this could become a mess pretty quickly? Because you could also have like a type 2. Do I show you these? No. Well, I'm not going to give you anything like this on the test. I just want you to know that these exist. You could go onto that wall, and why the hell not go on this wall too? You could have that happen too. So you could have all these different variations on these, where the shadow is being cast, which opens up the type of triple integrals you can do. We are going to focus solely on looking at solids that when you cast their shadows down, it's type 1 region, type 2 region, or polar. And then we'll get into spherical also, but that's a totally different kind of geometry. So we okay up to this? It's just like an FYI, just so you know, you could do it that way. And I ask you to do it here. We'll scrap this. Back in the day, I was a little ambitious that I thought I'd have time for doing it cast on different planes, but how about this one? Evaluate the triple integral of z dv, where E is the solid bounded by the cylinder, y squared plus z squared equals 9, and the planes x equals 0, y equals 3x, and z equals 0 in the first octant. Let's do this one. I'm not quite sure what this is going to look like. Where is this one? Okay. Okay, I'm trying to find triple integral over E of z dv. It's the solid bounded by, the region E is defined to be bounded by y squared plus z squared equals 9. And then x equals 0, which is the ground. Y equals 3x, which is a plane with a free variable of z. So it's a plane that's vertical, you could say, and it has some tilt to it. We'll draw it in a second. And then we have, what else? Z equals 0. And z equals 0 is the xy plane, and we're in the first octant. Octant 1. I'm going to try and draw this. Okay, I feel good about that. That's x, y, z. All right. Y squared plus z squared equals 9 is a cylinder. It should run parallel to the x-axis since the x variable doesn't appear. It should have a radius of 3, right? So this is like a cylinder coming down the x-axis, radius 3. Now, x equals 0 is the yz plane, right? X equals 0 is this back wall. So that should cut my cylinder off, shouldn't it? So I should have something like this on the back wall. 3. Do y'all buy that? And I'm not drawing in the other side of y because, remember, we're in the first octant, right? And then that extends out. You don't need to necessarily draw this, but I'll just kind of real lightly draw it. That, that cylinder kind of comes down like that, right? Do you kind of see that? Now, y equals 3x is a plane that we said was vertical. If I imagine on the ground, if y equals 3x is like a line on the ground, it would start off at the origin, wouldn't it? At 0? 0, 0. And then if I plug in 1 for x, what would I get for y? 3. So if I come out 1 on the x-axis, which would be here, it would come up 3, which would put me here, wouldn't it? Do y'all see that? And then I can imagine that plane would cut through the ground like that. Yes? Now that plane goes straight up, doesn't it? Straight up, straight down. Z equals 0 is the ground. Do y'all see the region or not? Do y'all see it? How could I draw this better? It's like a wedge. Okay, so I go from here up. I'm going to draw our region all in red. There. You agree that axis, that part of the z-axis is there? That back edge is there? Yes? This back side is there? This little front side right here on the bottom is there? And then I need to get from this point here to where? Well, we already know here, right? But where else does it need to go? It goes back to up here, right? but it's cutting my cylinder there. So it's going to look something like this. Do y'all buy that? Yeah. That's E. Now, the shadow on the ground, right there, can we draw that in two-dimensional space? We know that in 2D, it looks like this. This X value was 1 and the Y value was what? 3, right? That's that bottom piece. What type region is this? 1 or 2, right? 1 or 2. Do you have a preference? 1? Okay, so if I'm going to go 1, I'm going here like this. What's the top bounding thing here? Y is 3. And then what's the bottom bounding thing here? Y is 3x. Excellent. So can you list out real quick what are our restrictions on x and y over here? 0 to 1, y, careful. 3x to 3, good. And then over here, we need to get our top and bottom. Our top cap and our bottom cap is actually the ground, isn't it? So z equals 0 is the ground, and then the top, I need the equation of the cylinder solved for z. Square root of 9 minus x squared, y squared, thank you. And I only take that positive root because it's the top cylinder. I'm in the first octant. So my z here is between 0 and this. That's all I need for my triple integral, isn't it? So you can see where the heart of the problem is in the creation of the integral, right? The generation of the actual triple integral. After you get everything put together, it's really, there's not a whole lot there more to do. So I'm going to go 0 to 1. I'm going to go 3x to 3. I'm going to go 0 to root 9 minus y squared. What am I integrating? Z. I'm going d, z dy dx, right? Not quite sure I'd be too pumped up about this. Well, I don't know, because when I take the antiderivative that first time, I'm going to get z squared, right? 1/2 z squared. Then I'm going to plug this in, and when I plug that in, I'm going to square it, right? So the root's going to go away, so it's actually going to turn out nice. And work it all out, and you get the result. Okay? Questions? Please just make sure you understand that this right here is our function, right? This is our f of x, y, z. This is that hypersurface we can't see, right? It's somewhere that we can't imagine. These limits of integration just give us the restrictions on our solid. All right, I'm done. I'm not going to continue that one. So this just goes back to the whole idea of casting shadows on different planes. I'm not going to get into detail. Just make sure you know that they're there. And then this is our first application of this. I started the class saying, remember the application of double integrals? That if you do a double integral over some region, right, D, you do the double integral of 1, you get the area of the area of that region. If you do a triple integral of the function 1, the constant function 1, with respect to volume, then that will give you the volume of that. Right? So I think the last question is, what's the volume of the solid bounded by the cylinder, blah, 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 right? This is the same problem I just gave you. Notice I didn't give you a function like a triple integral. I just said, what's the volume of this solid? So if you wanted that volume, you would just need to set up a triple integral and then integrate the function 1. So it'd be exactly this problem, wouldn't it? Exactly the same thing, except z would be 1. And if you did that, you would get the volume of that little wedge. Make sense? I won't do it yet. We'll do it next class, but, well, we could kind of set it up. But I think this is probably a good place to stop. It's right there. That's the volume. I think so. I've done it before. 0 to 1, 3 to x. This is just the solid. Did you want the answer the one with z in it? Okay, so you want this one. Yes? Okay. So it was 0 to 1, that was the same. 3x to 3, 0 to square root of 9 minus y squared, right? And then dz, or z dz dy dx. 27/8. That's what I'm getting. All right. Make sure, yeah, there's nothing else. Let me just check our calendar real quick, see where we are. I think we fell behind a little, didn't we? Let's see. So today we're supposed to be starting, oh no, we're okay. 12/6, 12/7 was today. All right, so we just finished 12/5. That's all right. We're okay. Please sign in. I just put in this column right here 11-3. That's today. Just sign in right there, please. While you're signing in, I'll put a couple of problems or a couple of homework problems for you to look at. If Z is 1, it gives you the volume of E. It's another way that we can find volumes of solids, is using triple integrals. Just like you can use a double integral to find areas. Find the mass and center of mass of the lamina. So page 720, 5. I did that one. So 7's interesting. 10. 17. Yeah, that's 12.4. That's 12.4. Sorry, 12.4. Now 12.5. This is page 730. And I'm not sure if we've done everything in 12.5 that... I think you can do most of this. $11, $12, $14, $17, $19, and $20 is pretty good too. And the main thing you want to get used to is just trying to get the drawings of these things down, setting it up, drawing your 3D, getting comfortable drawing that 3D. All right, that sign-in sheet go around. Everyone have a good day.